Hi, everyone, and welcome to the second lecture of this series on winds in massive stars. So today we have the pleasure to have Dr. David Dickson. He's currently a postdoc in John's group at KULeuven. He did his master and PhD in Carolina State University in the US. And the topic of his PhD thesis was quantifying rush lobe overflow in the formation of merging black hole binaries. Graduated in 2024, and there is one paper in particular that I would like to advertise, which is hydrodynamic 3D simulation of rush lobe overflow in high mass X-ray binaries. So if you're interested, then just look at this paper. So today, David is going to talk about line-driven winds and mass loss recipes. So if you are ready, David, then the floor is yours.
Yeah, absolutely. Thank you so much. And thank you all for coming. Today I'm going to be talking to you about line-driven winds and mass loss recipes. But before I get into that main topic, I want to set up the motivation for what sort of sparked this whole field of interest. And that is a particular luminous blue variable called P Cygni. Um, while P Cygni is a peculiar object itself, these similar profiles have appeared in a lot of spectra that we've seen since. But in the 60s, when it was observed, it was rather a curiosity where we saw a emission peak from the stellar emission and a blue shifted absorption line. And this was on several key lines throughout its spectrum. Um, in the time since, we've seen enough other spectra show these P Cygni features to indicate that this is not some random intermediary cloud, but that there's some expanding outflow moving outward from these systems. And so the question really therein lies, what can drive this expanding outflow from the surface of these bright, massive stars? The mechanism that was proposed for trying to solve this is called line driving, a mechanism by which we take into account the absorption in this wind regime, which is going to be, of course, purely radial from the star, or at least predominantly radial, and consider the fact that the re-emission in that wind regime is not going to be primarily radial, but in fact isotropic. And that discrepancy leads to a radial net force as the surrounding wind or atmosphere of this star absorbs some of its emission. Uh, so that produces this P Cygni profile by the combination of this emission profile and the absorption, which we only see in the line of sight of the observer. So that's only the blue shifted part that we see in the absorption of it. This does artificially make the emission profile look like it's redshifted, look like it's shifted over in its wavelength, but only because we're only really seeing half of it. And so that solves that part of the question as well. Now, in order to have this line driving in the first place, this needs to be a significant enough net force to make a dent in the effect of gravity around the star. And particularly in order to drive it as an outflow that would get that blue shift, we need to see a significant reduction in gravity to even get into negative effective gravity, as it is called. Negative effective gravity is simply the net result of taking the contribution of gravity around the star and combining it with the force outward radially expressed by the radiation that is being absorbed in this line interaction. Um, and this can break hydrostatic equilibrium and lead to net mass loss so long as this effective gravity is negative. So, in order to get to those negative effective gravities, we're going to have to quantify what this contribution from the radiation is, which is going to be the sort of center of the next part of this talk, because there's a lot of math that goes into this. So I'm going to try and take it gradually and take you through it. So we're going to start simply. We're looking at the most hot, luminous, massive stars. So predominantly talking about O stars, but this also applies to several other types of stars in the same sort of regime. Um, we, of course, want to maintain our conservation laws. As I stated before, we're not hydrostatic anymore, so we're going to have to consider a radiative hydrodynamic approach. And we're going to generally start simple. So we're looking at the contribution of the star as if it was a point source in spherical symmetry. This is called the radial streaming approach, as it considers only that radial component contribution. And we're neglecting a lot of other complicated components to this, at least for the initial calculations. So these line-driven winds are powered by these absorption features in the wind. These absorption features are primarily categorized as either strong or weak. That strong lines, as you can see here in the middle, can have a significant impact. Those are the ones that are easiest to detect in observational spectra, but there's also a number of weak lines that have a much smaller impact on the total flux going through that spectrum. However, in such a large regime as this outflowing wind can be, uh, the fact that these deeper, stronger lines um, have a higher extinction is going to cut off their own intensity in the further out regime. So they're going to be self-limiting, whereas the thin lines are going to have low enough extinction to still see a driving intensity further out. So in fact, though the strong lines get a lot of attention in general, we have to consider all of the lines for a complete solution here. And considering all of these lines, we want to calculate one of three quantities, ideally all three, but those are the mass loss rate, terminal velocity, and force multiplier. The mass loss rate is critical to the evolutionary impact that we're discussing. So these systems are losing some amount of mass to generate this wind. And as that mass is lost across their lifetime, the end state of the star, or at the end of the main sequence, or at the end of its giant branch phases, is significantly different than what it was when it started that phase. And that's going to affect the distribution of outcomes of what happens next to that star. Um, but also we need to consider the terminal velocity, which tells us a lot of interesting things about what we would expect in observation, but is also critical to binary interaction. Um, in that, not to spend too much time on binary interaction here, but a secondary that is a wind accretor is going to have its impact on its interaction with the wind limited by that terminal velocity of the wind. And then the force multiplier is simply a measure of this sum of all lines to get the radiative force divided by what the radiative force would be if we just considered electron scattering rather than this line driving approach. So this force multiplier tells us how strong the sort of reverse gravity is in this region, the outward force. And that can tell us a lot about the profile with radius of what we would expect in this regime. Now that's a lot to solve, so we're going to have to take some key assumptions here. The one that is most common throughout these models that I want to discuss is the Sobolev approximation, which was previously detailed in the first lecture of this series. And that Sobolev approximation, as a refresher, um, assumes that the gradient of velocity is so high that we can only concern ourselves with the local region and treat everything as constant because that region is sufficiently small. So that is to say that the area that is in resonance with this outflow emission peak is small enough that we can use only local variables to define it. And in fact, we can use those local variables in an assumption of symmetry that allows us to cancel out some terms in the intensity here, neglecting the diffuse contribution. Um, and then we can use that to define what we end up with here as the Sobolev optical depth, which represents the amount of extinction across physical space observed within the wind. This optical depth is usually broken up into two components when discussed in some of the later papers here. So it's worth discussing those two components as the resonance quality Q here, which is a proportion based on the atomic properties in alpha line there. And this T, which is a characteristic optical depth at a given extinction ratio. So this is the extinction ratio, and this is simply the Sobolev optical depth, exempting all the factors that go into that extinction ratio. This T is defined in a few different ways, but particularly for here, I'm going to talk about this in terms of the speed of light c. You'll sometimes see a V thermal here, which I'll discuss as that comes up. All right. So with all those in mind, we can now calculate, given the Sobolev approximation and the spherical symmetry and all the other assumptions that we've made, a first estimate of the contribution to this radiative gravity through a single thin line. There's one last component that we need to contribute here, which is the weighting by its position in the flux spectrum. That is to say, the areas of the wavelength band that have more flux are going to be able to produce more outward force than the areas that have less flux and therefore have less interaction with the outflowing wind. And then we can apply a first order correction to get an estimate, again, using these initial assumptions to determine what a single line would contribute, even if it isn't a thin line contributor. I want to note that, as mentioned before, it is not just one line that is contributing to this outward force. We need to do a sum across multiple lines. So we would put this into a summation to get a more accurate contribution. The first paper to do that, to consider a sum of multiple lines contributing to this outward force, is Lucian Solomon in 1970. There had been previous works in radiative mass loss. However, they were focused on individual species. So for example, an iron line ejecting iron atoms rather than considering the propulsion of collective mass from the stellar surface. And they considered this without the Sobolev approximation. They were simply looking at a small number of species that were well defined, and so they didn't need that. Um, but they did take in a couple of assumptions I do want to talk about. They used plane parallel geometry, which is the assumption that the surface is flat and that everything is like you would do in kinematics, even though the surface of the Earth is a sphere. And so this plane parallel approach is fairly effective near the surface of the star, but not as effective at higher radii where that dispersion is going to be more impactful. And I also want to highlight that they only considered the strong lines of the particular species they were concerned with, which, as we've already discussed, is not going to give the full force that we might expect. So, unsurprisingly, we see a significant underestimate in the mass loss rates, but this is still a huge step forward in getting any calculated mass loss rate from line driving itself. And in fact, they found that theoretically, a single line sufficiently strong could produce negative effective gravity. However, practically speaking, the situations for that are so rare and niche that we really need a combination of multiple lines to produce a negative effective gravity that would cause this outflowing wind. And they considered only the most major lines, the resonance lines of these particular species. So they ended up with that underestimate. After Lucy and Solomon came the next wave of theories building on this that are known as CAK theories, particularly named for the paper by Castor, Abbott, and Klein in 1975. This CAK model takes some more robust assumptions, including spherical symmetry around a point source, as I mentioned at the beginning. It also does follow the Sobolev approximation. This spherical symmetry about a point source is still not an ideal model. And in fact, at the same places where plane parallel works best, near the surface of the star, is where this spherical symmetry works worst, because near the surface of the star, the radiation seen by that clump of gas, that parcel of gas, is not going to be purely radial, but coming from a number of different directions across the surface. But we're going to see more about that later. With these assumptions, the CAK model found that at least for C3, the resonance line by itself fit very nicely to a power law at 3 different temperatures here. However, when you count in all the lines in the relevant wavelength range, not just that strong resonance line, you get as much as 3 orders of magnitude higher force multiplier. So here you can see this force multiplier of 1 is here, and then it took a significant leap so that most of the bandwidth concerned, when considered in terms of all lines, was well above a force multiplier of 1, whereas that was not necessarily the case when just considering resonance lines. So they took their summation and put it into this power law fit. And it's worth noting the 2 components of this power law fit. The K parameter represents generally how many lines are contributing to the absorption region. And alpha tells us about the average strength of those lines. So alpha will be near 0 if they're all weak lines, and near 1 if it's all strong lines. All right. So they found, of course, force multipliers much higher, which will lead to higher mass loss rate than we previously saw with the Lucien-Solomon model. And that was a much better fit, at least to first order, with observations. However, they did fail to get a good fit to observations in terms of velocity. The terminal velocity fit that they had has a lot of room for improvement, we'll discuss in the next few slides as people built on this model. They put forward a finite disk correction, which is considering the star not as a point source, but as a disk of contribution. But we'll discuss that more when we consider models that do take it into account. In the 80s, Abbott expanded this model by applying it to a wider range of systems. So this CAK approach was applied to a variety of luminosities, metallicities, and temperatures, and found a number of dependencies here to a general fit. This notes that across a large portion of the regime, we get a systemic mismatch. So the M dots are consistently higher in this model than in observations. That while they're correct to the right order of magnitude, they are still significantly higher throughout the regime. Also noted that Wolf-Rayet winds cannot be fully explained by the CAK model. And I'm not going to go too in depth into the complexities of Wolf-Rayet winds, but that helped narrow our focus on them as research since has highlighted what interesting and unique things are happening there that aren't covered by the CAK model. There's also this delta parameter here. This 0.09 is called delta in some of the later works. And it represents how rapidly the ionization state changes with radial changes in, say, the ionization and recombination rates. And that factor ends up staying as one of those consistent parameters in later works as well. Moving right along to 86, Friend and Abbott took this finite disk correction into account that I was mentioning earlier. This is considering the force on this parcel of gas to not just come radially, but come from a variety of directions from a flat disk. So what a flat earther might model a star to be, which is at least a step up from considering it a point mass, and takes in these radial contributions, or non-radial contributions, excuse me. As you can see here, the non-radial contributions will cancel more and have a lesser effective gravity near the surface than they will out here, which leads to lower mass loss from the near surface region. But that results in more efficient mass driving out in the further away regions, where we see a higher terminal velocity because of it. They also examined rotation, but didn't find a significant effect on mass loss within the range of rotation that they were considering, at least. The other paper I want to discuss from 86 is the MCAK paper, a modified CAK method. This builds on what we saw with Abbott in 82 and of course the CAK method in 75. Also using a finite disk approach, but taking into account this delta parameter that Abbott in 82 gave us to represent the fit a little bit more closely. They did a comparison with another method called co-moving frame radiative transfer method, and found that at least in the narrow range that they were considering for that sample comparison, that the difference between the CMF method and the MCAK method was only in the very near surface region where the Sobolev optical depth approaches infinity. And that was a small contributor to the overall physics. So that was a sign of how robust this method could be, as CMF approaches are relatively much more computationally intensive, and therefore in the 80s, very difficult to do at scale. Moving into the 90s, we had a major shift in how these equations are represented, moving away from the K parameter seen before and moving towards the Q notation of Gailey 95. This uses Q naught to represent an effective maximum that the force multiplier can reach due to a high saturation limit. So that is to say that the force multiplier cannot raise to infinity because at some point you will have saturated your spectrum and blocked out your ability to interact with the wind further. And then this is used to define a Q bar that more directly replaces K here in the multiplier equation. And this Q bar is weighted by the flux and population, replacing K, which was counting the number of lines, with something that is more analogous to a line strength cumulatively across the spectrum. All right, and that gives us the foundations to talk about the 21st century here. Moving into recipes that are still in use today, I want to start with Vink et al. From the turn of the century here, which was not a CAK method. It still follows the Sobolev approximation, but it followed a Monte Carlo method instead of CAK. So using these randomized Monte Carlo models, they looked at a variety of metallicities and stellar types. And the benefit of this Monte Carlo method, or one of them rather, is that it allowed them to also take into account multiple scattering. Multiple scattering is the effect where some percentage of the incident light that is absorbed by a parcel of gas in the wind regime is re-emitted past the edge of the donor star here and interacts with another parcel of gas in the same spherical shell of that resonance zone. And so that means that same incident photon can lead to contributing to momentum in multiple places, even if its contribution to energy is the same. And this approach, this multiple scattering contribution, has changed the way we look at the velocity profiles in these wind regimes, but there are still some other factors that it doesn't address. And I want to move forward to more recent work here with Kratukka and Kubat, which used this CMF, this co-moving frame radiative transfer consideration that addresses not only this backscattering, multiple scattering effect, but also allows a better consideration of effects like continuum reduction and overlapping lines, where the effect of one line's extinction can affect other species' experience of the incident light as well. So in the continuum reduction case, for example, if you have enough saturation of lines, you can effectively reduce the entire continuum to the point that outside of any individual species, the incident light is significantly lessened broadband. I also want to note here that the CMF approach is going to be described in greater detail in another lecture. So if you want to learn more about that, you can come back for that lecture as well. This approach notably expanded across main sequence giant and supergiants, and was built on by Bjorklund, which also included dwarf stars and a wider range of metallicities. And this follows that same CMF radiative transfer method, but across a larger set of species, giving a wide range of reference values for observers to compare to. Moving back to the Sobolev approximation from the CMF, our group here at Leuven recently put out the LIME method, which is a publicly accessible tool online that rather than giving a table of reference values from calculations done in advance, does calculations directly with the chemical composition and stellar parameters of a specific star, and follows the MCAK method, a modification of the MCAK method previously discussed. And because of this on-the-fly approach, this line model is able to fit not just different metallicities, but more unique chemical compositions, where, for example, you have an overabundance or underabundance of a particular element compared to what would be the standard for that metallicity. I want to highlight in this figure here that we see the order of this axis is flipped. So this power law here is the same shape as the power law we saw in the opposite direction in the previous figure of CAK. But here you see the Q naught limit maximum here from saturation, giving it this hockey puck shape, hockey stick shape rather. All right. So that gives us two regimes of modern recipes to compare, those based on the Sobolev method and those based on the CMF method. To just briefly remind, the CMF method is able to account for some second order effects in much greater detail, but does take a much greater computational cost to model in the first place. So because of that, even to this day, one of the most commonly used models is the Vink models from 2000, which has a wide range of papers that you can compare your own observations to because of that commonality. But the CMF approaches have some distinct advantages, and particularly the Sander and Vink paper I have not yet mentioned, but it is mostly specialized on Wolf-Rayettes, which is why it's not quite as relevant here, but it builds on the range between fully thin or fully thick winds as well, leading to some potential future research there as well. Looking from the present to the future, we do have some remaining things to work on in this field. The 3D effects, so for example, a over density or under density in some particular region called clumping usually, but also the difference in wind driving from the polar region versus the ecliptic. There's a number of 3D effects that have not yet been modeled into these self-consistently, which could be very helpful to 3D or 2D simulations that want to use these self-consistently as well. And while there has been work in clumping, rotation, and magnetic fields, there's still a lot of work to be done in building on those to give a better fit to what we're observing. Um, and thermal velocities are still a bit of an unknown factor, which is why I chose to use the definition of the characteristic optical depth based on the speed of light rather than based on thermal velocity, because the way those are defined from one work to another are not fully consistent yet. So there's some work left to get a better definition of how those should work. And of course, there are some systems like Wolf-Rayette's that are not well fitted to this model and still need their own exploration as well. Thank you so much.
Thank you very much for this very nice talk. Um, do we have question in the audience? A lot of applause, but I don't see question yet. Maybe the audience is digesting slowly the talk, but anyone wants to ask question about it? Maybe Joe? No, you.
Yeah, can you hear me?
Yes.
Yep.
Okay, good. Thanks for this very nice overview. It covered a lot of things, and I was in the beginning a bit skeptical to have both the basic theory as well as the modern recipes in one talk, but you did it very well. So that was really surprising for me that one can do this in 40 minutes. So thanks a lot for this overview. I just wanted to have one or actually two comments. The first comment is related to the second one. When you spoke about the CAK theory, you mentioned that the diffuse radiation field is neglected. Actually, this is only, how to say, not completely true, because in Sobolev theory, the diffuse radiation out. This was shown in block 1 of our lecture series. So you do not need to consider it, because in Sobolev theory it cancels out. However, then, of course, Sobolev theory, as you also told us, is only very valid under very specific conditions, particularly in those regions where the curvature of the velocity field is not very large. And this curvature effect, of course, is then strong when we have a curved velocity field, which happens typically in the sonic region of a stellar wind. And then the Sobolev theory somewhat breaks down. And in parallel, the impact of the diffuse radiation field is increasing. So basically, it's not the Sobolev theory per se, but the impact of the diffuse radiation field, which is coupled to this kind of curvature effects. And therefore, this is something which makes a major difference for the radiative acceleration in the sonic region. And this is one of the major differences between these Sobolev kind approaches, as Monte Carlo approaches, CAK, PPK, and so on, and the other approaches which you have mentioned by Kritichka or by Sanders and so on, or by Sundquist and so on. So all this goes down to the point that the impact of this diffuse radiation field, so more or less the asymmetry of the scattering process, that this plays a major role. So this was my comment on this. Thanks a lot.
Yeah, absolutely. Yeah, and it's worth noting that, as he said, that the treatment of that diffuse contribution, it only cancels out in this basic model, but that for example, the CMF, the co-moving frame model doesn't have that cancel out and sees a net reduction in force throughout as the that curvature is taken into account. Yeah.
Since we were on this, may I add a follow-up comment here?
Yeah, of course.
I could not. I tried to raise my hand, couldn't find the the bottom. You know, after 5 years, one would think I could, but anyway. I think this is something that, you know, David didn't talk about, but related to that comment, there is actually still the open question, at least in my opinion. These are all stationary models, right? And in those, you have to derive the mass loss rate from some sort of condition. And this in the CAK model is quite different than in the co-moving frame models, in the sense that if you do it from a critical point analysis, it is not the same because of the explicit dependence on the velocity gradient in a CAK type of model. Actually, the velocity gradient is power law of alpha, right? Whereas in the co-moving frame models, that doesn't enter, such that the very basic point where the mass loss is, so to say, set of the wind, the choke, the hourglass, if you will, is basically down in this region, which Joe mentioned, where these curvature effects are important, right? And this may be a major contribution to why, you know, for example, often we see a little bit lower for at least some stars that are not so thick winds in the co-moving frame approach. You have a force reduction there, as also pointed out in one of the slides of Davey, right? Whereas in the CAK model, where you have the explicit velocity gradient, yeah, this analysis is different, right? Because that's no longer the choke of the wind, the critical point on the wind. And this, in my opinion, is that makes it different from solar wind theory as well. And it's still it's sort of say an open question. One could argue that it's just a mathematical question because, you know, who cares about the critical winds in the station, critical point in a stationary wind? But for the models, it's actually for the model building, it's very important. So I would say that this this has been an argument. Joe can probably, and the more senior here, they can have been in the business longer than me. They can point out that this was argued already for 30, 40 years ago, I think. And in my opinion, it's still around. I don't see as, yeah, it's not an easy way to solve this, at least not in my view. So since we're talking about the basics here, there's also some some real basic work that could be done there, I think.
Thank you for the discussion. Do we have a comment related to that or other non-related questions? Doesn't seem to be. So that's your very last chance to ask Dave a question. Nope. Then I think we can thank the speaker again. And we meet for the next lecture next week.